Page 374 is brought to us by Bearded Nightman with, it looks like he's got a belt on over his chainmail, which is interesting. And he looks a little tired. Look at those lines under his eyes. So we're looking at empirical probability now, which is a calculation using experimental data rather than all these equally likely outcomes. So an example here, real quick example, let's say out of the last 100 days you went to the gym 60 times. So you can build a probability of the likelihood you're going to go to the gym tomorrow as a 60% chance, because out of the last 100 days you went to the gym 60 times. 60 out of 100 is 0.6. That's an empirical probability. It's based on observed frequencies. Number of times you went out of the number of times you didn't go, total. So it turns out, theoretically, there really were only two possibilities, right? There's a 50-50 chance you go to the gym or you don't go to the gym. But it's not particularly useful or as useful as the fact that in the past, this is how often you went to the gym. So we use this a lot. At Jackson College, it's used. We try to determine how many classes should we offer, how many sections of a class. And so we look at, say, how many graduating seniors are there in the local high schools, how many people are going into particular programs that need this particular course, and we build that. So we use current population data to try to decide how many sections should we create. You could try this on your own. You could flip a cup and calculate how many times, or keep track of how many times the plastic cup landed side up or side down, and then create some empirical probabilities. Generally speaking, this is how we calculate that probability. It's the observed frequency of the event, we call that F, divided by the number of trials, we call that N. So here's an example. We're skipping all this because we're not together. Here's an example of from earlier, where we had the observed frequency of going to the gym 60 times. We had not going to the gym 40 times, and the total was 100. This would represent our N. And if we wanted the probability of the gym, right, we did 60 out of 100. If we wanted the probability of not the gym or no gym, that's 40 out of 100. Here's another example. We've got the type of a blood type. So we're looking at type O. There were 210 people that had this blood type. We had type A here, 223. We've got type B, looks like 16. And we've got, oh boy, I got that wrong. And we've got type AB, which is 16. This one was supposed to be 51. So this is a table of data. Note that the sum, this little symbol means it's sigma, it's called the sum. The sum of all these is 500. That represents the number of trials. 500 people in our sample. These are the observed frequencies that result for each of these. Our author has given us a nice look at who can donate to who. And we're going to use this table, this empirical set of data, to calculate these probabilities. So what's the probability that a randomly selected patient can receive only one type of blood? Well, let's look. Who can receive only one type of blood? It looks like type O patients have only one arrow going to it. They can receive only one type of blood. So we're calculating the probability of randomly selecting a type O patient. Based on how we calculate probabilities, that's the 210 in our frequency, observed frequency, by the 500. We're going to talk about a little bit later about how this rolls out, how we can infer this to a population. But this looks like 0.42 or a 42% chance. when we randomly select someone out of this sample, there's a 42% chance that they can only receive one type of blood. How about if we've got an accident, a victim has type B blood, and an EMT is on site, is the only person willing to donate blood? What is the probability that it will be compatible with the victim? Okay, well, a victim that has type B blood can only receive blood from someone who has type O and type B blood. So we need the probability, well, I guess what we need to note is that this person can receive O and B. So there's 210 plus 51 blood type. So 261 options from our sample that they could receive. So the probability that they are compatible, the person who's willing to donate, there's a 261 out of 500 chance based on our empirical probability. I will again type that into my trusty calculator, 261 divided by 500, and I'm getting, there's a 0.522 chance, or a 52.2% chance that that EMT would have the correct blood type and be able to donate to that person. Okay, if a person had blood type A and they get a transfusion, what's the probability that the donor was not type A? So let's start with type A. They can receive from type A, or they can receive from type O. So they can only receive from those two types. So what we're looking at is, are they receiving from a type O person, right? That just means, it looks like to me, what's the probability that the blood donation that they're getting is from type O? We already calculated that number prior. 0.42 or 42%. Okay, find the probability that a randomly selected donor's blood can be given to patients of more than just one blood type. Okay, who can give to more than one blood type? Type O can give to everyone. Type A can give to A and AB, and type B can give to B and AB. So it's these three types can give to more than one type. So we could calculate this two different ways. We could add up O, A, and B, and that would be it. Or we could just do 1 minus the probability of AB, which is the one I'm going to do. Because AB is the only one that can give to only one type. So we're going to say 1 minus not AB is the probability you can give to more than one type. So that's 1 minus 16 out of 500. I'm going to do this one again in Desmos. 1 minus 16 out of 500 is this, there's a really high chance that we select someone and they can give to more than one type. There's a 96.8% chance. Note, if we wanted that as a fraction, I can click this. Desmos automatically simplifies that fraction, writes it in lowest terms. I don't know that that's necessary. I wrote it down as 96.8%. So to end this, let's just look at these little scenarios and decide, are we working with something that's theoretical, where we know all of the outcomes and it's non-data, or are we working with something that's empirical, where it's a data set? So we could say theory, or known outcomes, or a data set. So we got the probability of a high school basketball player one day being drafted by an NBA team is this. Incredibly low. This is from a data set, so it's empirical. And what this data set is, they took all of the high school basketball players that got drafted into the NBA, divided by all the players that were in the NBA. This is that probability. It's a very small amount. What, LeBron James and one other person? Okay, the probability of being dealt one pair in 5-card poker is this. That's theoretical. We know all of the cards in the poker deck. We can calculate all of the probabilities of something happening. This isn't we dealt a bunch of cards and have a data set of how often one pair is dealt. The probability of being in a fatal accident if you make 2 car trips a day for 1 year is this. Well, this is data, more or less. If you've never been in a car accident, it's not data based off of you, it's based off of all drivers and all the accidents that happen. The probability of winning some prize when buying one New York State Lottery scratch-off ticket is this. Ooh, this is a tricky one. Because scratch-off tickets, like, things are randomly printed on them. And I don't know that we know all of the possible outcomes on a scratch-off ticket. It's different if you're, like, selecting numbers. Like a pick 3 or pick 6, because we know all the number calculations and we can calculate easily the probability of a number being drawn. But scratch offs, someone's printed all these tickets. Well, you know what? I think I'm going to go with theoretical on this, because when the printers print the scratch off ticket, some winning numbers have been printed somewhere. There is definitely a printed winning scratch-off ticket somewhere, and the computer is probably programmed to print it, and we know how many winning tickets there are, and so we know this number is calculated off of the known odds of winning.